To introduce the idea of numerator dynamics, or functions of s in the numerator of a transfer function, let's consider a differential equation that gives rise to what's called a lead-lag element in the Laplace domain. We did an example like this in class a week or so ago. Here, y and u are both functions of time. When we take this into the Laplace domain, and we find the ratio of the output y to the input u, we obtain a tau s plus 1 term in the numerator and a tau s plus 1 term in the denominator. We call this type of transfer function a lead-lag element. What is the response of this transfer function to a step input with a magnitude m? To find the output, we take the input function m over s and we multiply it by the transfer function. Then we can perform a partial fraction expansion, which will have a constant over s term and a constant over tau s plus 1 term. We can use the Heaviside method to find out that the term a here is tau a minus tau 1. When we invert this back to the time domain, we find an exponential decay. Now we can ask the question, how do the values of the poles and zeros affect the output? The Laplace domain expression for the output function of a step input to the lead-lag element is shown here. This function has 2 poles and 1 zero. The pole P1 represents the pole at s equals 0. In the partial fraction expansion, that would represent a constant term. So P1 ensures that there will be a steady state gain. That is, in response to the step input, the final value of the output will be different from the initial value of the output. The pole P2 is minus 1 over tau 1. That pole has a negative real part, and its magnitude determines the kinetics of the approach to the steady state. That is, how fast this exponential term decays. The zero is at minus 1 over tau a. We can consider different classes of behavior for how this value of the zero affects the output in the time domain. Here, we've plotted in the complex plane 3 different cases for values of the zero. In case I, the zero is between the origin and the pole at minus 1 over tau 1. For that to be the case, tau a must be larger than tau 1. All of the cases shown here are plotted for tau 1 equals 4. So we chose a tau a of 8. When the numerator time constant, tau a, is greater than the denominator time constant, tau 1, then the initial response to a step input will go past the final steady state and then decay to the final steady state. We call that behavior overshoot. So when tau a is greater than tau 1, this ratio is larger than 1, which makes this coefficient on the exponent positive. That gives rise to the overshoot seen here. When tau a is between 0 and tau 1, then this ratio is less than 1, so the coefficient on the exponent is negative. In the time domain, the response to a step input will be an initial step towards the final steady state, followed by an exponential decay to the final steady state. The last class of behavior is when tau a is negative. When tau a is negative, the zero at minus 1 over tau a is positive and real. The positive real zero gives rise to a behavior we call an inverse response, where the initial response to a step input is in the opposite direction of the final steady state, followed by an exponential decay to the final steady state. The examples shown here are for values of tau a of minus 1 and minus 4. So the step response of a lead-lag element can have overshoot, in which the initial response to the step input goes past the final steady state and then decays to the final steady state, or it can have an inverse response, in which the initial response to the step input goes in the opposite direction of the final steady state and then exponentially decays toward the final steady state. So the zero determines the direction of the response, but has no impact on the kinetics. That is, the time that it takes for all of these to approach the final steady state is governed by tau 1, or the pole, whereas the direction is governed by tau a, or the zero. What kinds of physical processes can give rise to these sorts of lead-lag elements? In the next video, we'll give a simple example of a physical process that can give rise to a transfer function that looks like this.